Hi, in this video, we're going to talk about single rotation in AVL tree, which is a way to keep the AVL tree balanced. So whenever we study data structures or algorithms, it often helps to think about what is the simplest problem we're trying to solve first, right? So in the case of AVL tree, then the question is, what is the smallest binary search tree that does not satisfy the AVL tree's invariant? So let's look at one of the simplest possible binary search tree, a tree with a single node. Does this satisfy AVL trees invariant? Well, the answer is yes, it does, right? It doesn't have a left nor right subtree, and so they are the same height. So as a matter of fact, this is a perfectly balanced binary search tree. So that's great. Okay, what about the next one? Binary search tree that has two nodes, like this one. Is this an AVL tree? Well, yes, it is, because if you look at the left subtree, it has height of 0. Now, if you look at the right subtree, it's not there. So, I mean, there's no way for the left and right subtree to be differ, the height to be different by more than 1. Now, when it comes to implementation, when the subtree doesn't exist, we'll initialize it to -1, but we'll see more of that when we get to the implementation. Now, one thing to note is this is, even though this is the AVL tree, it's not perfectly balanced. And there is no way to make it more balanced than it already is, right? Even if you put the 2 on the top, then the 3 is still going to be one level below 2. So there's no way you can make it more balanced. So as a matter of fact, it's not difficult to prove that if you want a perfectly balanced binary search tree, the number of nodes must be some number, 2 to the some power minus 1. Okay, and that is there are not too many numbers like that, right? There's the number 3, 7, 15, and so on and so forth. And in practice, you're not gonna, most of the time, we're not gonna have that exact number of nodes to make a perfectly balanced binary search tree. And that's actually why, if you remember one of the questions from earlier, is that why the AVL tree does not require the both subtrees height to be exactly the same, because it's pretty hard to achieve. So the AVL tree invariant is more relaxed than a perfectly balanced binary tree would require. Okay, next one. Think about this one now. Now that we have 3 nodes, is this an AVL tree? Well, it's not an AVL tree, and because the left subtree of 3 is height of 1, and well, but there are 2 nodes, right? You can see that, and the right subtree, there's no right subtree, so this is more than two levels higher than the right subtree. Okay, and so we want to fix it. We want to fix the imbalance. How do we fix the imbalance? Well, before we fix the imbalance, one thing I want to point out is in many literature, and I think including ours, this is referred to as the left case, because starting from the node that has an imbalance, the problem stems if you travel down the left subtree and then the left subtree again. So this is the left case for a binary tree that is not a AVL tree. Now, how do we fix that? Well, fixing it is pretty simple. We do what's commonly referred to as a rotation. We just rotate the tree to the right in this case. So if you look at, we start with this one, and when we rotate, we're keeping 2 and 1 in exactly the same spot, right? 2 and 1 is not changed. However, the edge between 3 and 2 gets changed. 2 comes to the top, and and 3 becomes the right child of 2. And 3 can become the right child of 2 because 3 is bigger than 2. Right? So what we end up with is a tree that contains the same data as the original one, and everything is still in the right order. It's still a binary search tree, and now it's a balanced binary search tree because now this left subtree and the right subtree are at the same height. And the mechanism to do this is, it looks like a rotation. That's why it's typically called a rotation. But remember, that is only just a way to talk about how to reduce the height of a binary search tree. So the important thing, remember what the goal is. Keep the same data, keep the same order, but make it more balanced. All right, so having seen that, I present you another case, and that is actually very similar to the previous case. It's just the mirror image of the previous one. So where the previous one is a left case, this one will be the right case, or the RR case, some like the abbreviation of that. So work out how you would make this into a AVL tree. And here is how you do it. So we are not rotating to the right this time, we are rotating to the left this time. Okay, so same thing between 2 and 3 is still exactly the same, but now we bring down 2, 2 becomes the left child of, 1 becomes the left child of 2, and because 1 is less than 2. That's it. Okay, there's a slightly more complex exercise for you. So think about the original tree that looks like this. It does not have the 0 yet, okay? See the dashed line here. So the original tree is just 1 through 8. Okay, and now and that is actually proof to yourself that the original tree is an AVL tree. Okay, and the next thing that happens is we're going to insert 0, which is going to come hang off here. So, and also, if when that happens, prove to yourself, convince yourself that the new tree is no longer an AVL tree, and we want to make it into an AVL tree again. So, how would you fix that? Okay, and here is the answer. Because the imbalance actually occurred at node 2, and then we look at it, this is going to be a left case, so we do a right rotation, we bring up so 1 is going to become the root of this subtree here, right? And the relationship starting of all the numbers starting from 1 and 0, that's it in this case. That's nothing changed there. What's changed is the relationship between 1 and 2, and 2 now becomes the right child of 1. Everything is still the same, all the order is the same, the data is the same, but now the tree is more balanced. Okay, and another thing I want to point out is that when you look at where the imbalance actually occurs, it actually not just occurs at node 2, also at node 3 is also there's an imbalance, right? Because there are 3, the subtree here, the height is 2, and the right subtree of 3, the height is 0. So 3 is also imbalanced, and 5 is also imbalanced. But we want to fix the one that is the lowest in the tree. So in other words, we want to fix the imbalance from the bottom up for 2 reasons. One is because heights are calculated from the bottom up, so it's kind of very natural to sort of start fixing things from the bottom. And also because, again, how the heights are calculated, if you fix something that's higher up in the tree, it doesn't necessarily change the height below it, and therefore if there are imbalances below it, then fixing things higher up might not necessarily fix the imbalances below it. So that's why even though there are multiple nodes that are unbalanced, we fix the one that is lowest in the tree.